Welcome to The Explainer. Today we're going to plug in and really get to grips with the force that powers, well, everything, electricity. We're going to break down the basics, and you know what? It all starts with a really simple idea. So what actually is electricity? I mean, really. If you want to understand how your phone charges or even how a light bulb glows, we've got to peel back the layers a bit. And it all starts with one super simple but really powerful analogy. Okay, here it is. It all starts with a simple flow. Just picture this in your head for a second. Water moving through a pipe. Got it? Good. Because honestly, that one image, that's the key. It's going to help us unlock everything else we talk about today.
So that idea of a flow, that brings us right to our very first big concept. Only instead of water, we're talking about something called electric current.
So what is it? Well, an electric current is basically just a huge number of charged particles. We're usually talking about electrons, all moving together in the exact same direction through something like a copper wire. You can almost think of it like a one-way street during rush hour, just a massive traffic jam of energy all heading in the same direction. And the scale of this flow, it's mind-boggling. I mean, to get just 1 ampere, which is our standard unit for current, you need this many electrons, 6.24 times 10 to the 18, to zip past a single point. Every single second. That's more than 6 quintillion. It's a rush of particles that's almost impossible to wrap your head around.
But, you know, a flow like that doesn't just happen magically. It needs a push, right? And just like our water in that pipe, it's always going to face some kind of resistance, some opposition along the way.
And that's where 2 other key players come onto the scene. You've got voltage. That's the push. It's the electrical pressure, the force, that gets that current moving in the first place. You can think of it as the pump. And then you have resistance. That's the opposition, anything that tries to slow the current down. It's like a narrow section in our pipe, kind of pinching the flow. So now we've got these 3 things, right? Voltage, current, and resistance. And what's so cool is that they're all connected. They're locked together by this one really elegant and simple formula, Ohm's law. For most basic circuits, this thing is the golden rule.
And you can see that law in action right here. It's pretty straightforward. If you want more current, that's the I, you've basically got 2 levers to pull. You can either crank up the voltage, the V, to give it a bigger push, or you can lower the resistance, the R, to make the path easier. It's this constant balancing act.
Okay, so let's move from the concepts to the real world. Let's look at the actual physical parts that create these effects in a circuit. You know, the components that give us that resistance and that voltage.
So if you take a bunch of resistors and you line them up one after another, just like this, you've got what's called a series circuit. It's a single file line. The current has absolutely no other choice but to go through each and every one. So to get the total resistance, you just add them all up. Simple as that.
But what if you connect them in parallel? Now you're not making a single file line, you're opening up new lanes on the highway. This gives the current a bunch of different paths it can take, and what's really cool is this actually lowers the total resistance of the whole circuit. I mean, it makes sense, right? More paths means an easier trip for the current.
All right, so that's resistance. Now let's look at the other side of Ohm's law, the voltage generator. We're talking about your battery, your power supply, whatever's providing the push. Now, in a perfect textbook world, a generator would give you a perfectly constant voltage no matter what. But we live in the real world, and in reality, every single power source has its own little bit of internal resistance. And that means when it's under load, when it's working hard, the voltage it supplies actually dips just a little bit. Okay, so we've got the players, voltage, current, resistance. We've got the parts, resistors, generators. Now let's look at the rule book. The universal laws that every circuit has to follow, no exceptions.
And these are Kirchhoff's 2 fundamental laws. They're absolutely essential. The first one, the node law, is super intuitive. Whatever current flows into a junction has to be the same amount that flows out. You can't just lose charge along the way. The second one, the loop law, is about energy. It says if you go in a complete circle around any loop in a circuit, all the voltage you gain from your battery gets used up or dropped by the components. It all has to add up to 0. In other words, energy is always conserved.
Now here's something really important to remember about resistance. It doesn't just slow the current down, it actually does something with that energy. It converts it into heat. We call this the Joule effect. And you've felt it. It's the whole reason your phone charger or your laptop adapter gets warm when you use it.
That heat, that's basically the cost of doing business in an electrical circuit.
And this just drives home that point about conservation. It's a strict, unbreakable rule. The amount of power that the generator puts into the system has to be exactly equal to the total power that's used or dissipated by all the parts, like our resistors, turning it into heat. Nothing is ever lost, it just changes form.
All right, let's put all these pieces together. Let's watch a real and very common type of circuit in action. It's called an RC circuit. And as you might guess, it uses a resistor and another cool component called a capacitor.
So here's what happens. The moment we flip that switch, bam, current starts rushing out from the power source. But it doesn't just flow through the circuit. Instead, it starts getting stored up inside the capacitor. It's kind of like filling a bucket with water. And as that bucket, our capacitor, gets fuller and fuller with charge, it starts to push back against the flow, and the current slows down and down until it eventually stops. But what happens next is the really neat part. If we then disconnect the main power source, that charged-up capacitor suddenly becomes its own power source. It's like a little temporary battery. It releases all that energy it was storing, pushing a current back out into the circuit until it's completely empty again. This whole charge and discharge cycle, it's the basis for so many things, from timers in your microwave to filters in your stereo. So there you have it. We've covered the fundamental rules of the road for simple circuits. We've talked voltage, current, resistance, but our story isn't quite finished. There's a huge key ingredient we haven't even touched yet. What happens when you throw magnetism into the mix? Because that's when electricity truly becomes a force of nature. It's what creates the power to spin motors, to light up cities, to run our entire world. And well, that's a story for another explainer.